Hello, everyone, and welcome to another wonderful day of PChem. So today we're going to continue our conversation on the rigid rotor. So last time we built up a system of uh, descriptions of angular motion, and we're going to essentially try and apply that to get a eigenfunction and an eigenvalue of a rigid rotor, which is essentially a rotation of a molecule with a fixed bond length where one atom forms the center of mass. So to describe this system, we can essentially start with our uh, Hamiltonian for a rotating free particle with, again, fixed distance. So we have as constants, our Planck's constants, our mass, which should be done as a reduced mass for most systems, and again, our bond length of the system. And we're then going to essentially apply a variation with angle to our wave function. Now, we can go ahead and condense this more general set of constants by realizing that our mass and our distance can essentially condense down to a simple moment of inertia. Now, this forms a eigenfunction eigenvalue system, and it turns out that there is a known set of eigenfunctions for this Hamiltonian, which form the general structure of a normalization constant times the exponential times an imaginary number times a new vibrational quantum number, which we are going to call a rotational quantum number that we are going to call m sub l for reasons that we will see next chapter. And again, the location of the particle in the direction phi. Now, this should look vaguely similar to our eigenfunction for a free particle, because again, the major changes here is going to be a new quantum number, and that instead of x, we're dealing with phi. However, with this general form, and again, it is worth noting that we no longer have a constant of k present either. Now, not too surprisingly, we are going to find an energy similar to our one-dimensional form. Again, this time missing a constant k. So the energy eigenvalue for a rigid two-dimensional rotor can be given as our rotational quantum number squared, Planck's constant squared, and then again twice our moment of inertia instead of mass. Now, here's going to be the big problem. This, as I said, is going to be our rotational quantum number, but what values of m sub l are going to be allowable? Now, this is a pesky issue, but we can actually determine this using a similar trick that we did for a one-dimensional system, which is starting with the idea of let's set some boundary conditions. Now, boundary conditions for a rotating system are going to be a little bit different. So here, our only major constraint is going to be that the function is going to be equal at phi as it is at phi plus 2 pi. This means when I complete one complete rotation, my equation should continue smoothly. And this should be true for both my real and my imaginary part, because as a reminder, we can break using Euler's equation, we can go ahead and break this exponential down into a cosine and sine function with a real and imaginary function. So real cosine, imaginary sine. And this is going to give us a rotating behavior. The diagram provided here is for, I believe, for a value of m sub l equals 1. However, what we want to go ahead and figure out is what values of m sub l are allowable. And we can do this by applying this boundary condition. So let's go ahead and plug in our equation. So on the left side, we have our simple wave function. On the right side, we now have a theta plus 2 pi inside of our exponential term. Well, this is a little bit pesky. So what we can then do is use our go ahead and factor the system out. So now in the exponent, I got I m sub l phi plus I m sub l 2 pi. Then using our exponential rules, we can separate this into two separate exponentials. So when we do this, you'll note that the first set of terms is just returning our wave function, where we have the normalization constant times our exponential with respect to m sub l and phi. However, we ended up generating an extra exponential function dependent on an imaginary number, m sub l, and 2 pi. Well, this is going to be a little bit problematic. However, we can essentially substitute out the system. Again, using our exponential rules, we can pull out the 2 pi as a power. So this is going to be the same thing as e to the I pi times, 2 times the rotational constant. We get to pull that out. This one is where we finally get to use Euler's identity, because e to the I pi is the same as -1. So what I have is, by applying the boundary condition, I have my wave function equal to itself times -1 times twice the angular momentum quantum number. Or sorry, the rotational quantum number. Now, this is going to be a little bit pesky, because I can only have this equation be true for certain values of m sub l. And the ones that work are going to be pretty much any real integer. Because if I have a value of 0, well, I have -1 to the 0. That works, because that's just 1. If I have -1 to, say, the power of 2, so m sub l equals 1, well, 2 works, because then I get +1. Same thing will happen for 2, 4, 6, 8. So as long as m sub l is an integer, we're good. But here's actually the cool part. It can be negative as well. Because if this value is -1, well, -1 to the -2 power is still 1. So whether m sub l is positive or negative, this equation will work as long as it's an integer. So this sets our values of m sub l that will actually work. This leaves us with only one mysterious part of our equation, which gives us a set of discrete energy values and leaves us with only one mysterious part of our wave function, the good old normalization constant. So let's go ahead and normalize our wave function. So again, normalization can be given by integrating the system over all space. Well, all space for a cylinder is 0 to 2 pi. Those are the only values for phi before we essentially repeat ourselves. So we can then input our complex conjugate, e to the negative I m sub l, and then our actual value, e to the I times the quantum number times phi. Now, this is one of my favorite integrals because, all right, if I multiply these two together, that's the same as adding the exponents. So I times the quantum number times phi minus I times, yeah, that goes to 0. So when this goes to 0, well, any exponential of 0 is 1, as we already demonstrated. So then I just have the integral of d phi from 0 to 2 pi, which is just the same as 2 pi minus 0, so 2 pi. So as a result, when we normalize the system, we get 2 pi times the normalization constant squared equals 1. Now, one of the things I want to emphasize is this is not dependent upon the value of m sub l. So no matter our quantum number, no matter our rotational state, we're always going to have the same normalization constant. Gotta love it when that happens. So we can then divide both sides by 2 pi and then take the square root. So it turns out that our normalization constant is simply 1 over the square root of 2 pi, no matter the state. So our resulting wave function is in the general form, just going to be our new normalization constant times the exponential of I times our quantum number times phi. And our quantum number can range anywhere over over any real integer, positive or negative. So it's quite an impressive little series we have here. So this gives us an actually pretty robust description of 2D rotation by a rigid rotor. We have a wave function, we have an, sorry, my mouse spazzed out on me there. We have a wave function, we have a set of energy levels, and we have the permissible quantum numbers. However, let's go ahead and take a look at what this looks like in terms of energy numbers, and this will kind of give us some fun implications. So first of all, unlike our unlike vibrations, it's actually possible for a system to have a zero rotational energy. So it's entirely possible for a system to just simply not rotate. You don't have to have rotational energy to be a molecule, because if m sub l is 0, then the energy term just drops out. Then if I have a value of 1, energy is just going to be h bar squared over twice the moment of inertia. However, here things get a little bit fun, because from here, if I go to positive or negative 2m sub l, what we end up having is 4 times h bar squared over twice the angular momentum. Then when we go to 3, it becomes 9. And then when we go to 4, it becomes 16. So what we tend to see is that our energy levels become increasingly separate as we go up rotational quantum numbers. Also, a very important feature that we haven't encountered yet is going to be this idea of degeneracy. So we did not have this with our vibrational numbers, but it turns out there's 2 different ways to get rotation. Essentially, forward motion, positive, or reverse motion, negative. So as a result, all of our energies, except for the ground state, are going to be doubly degenerate, because there's only one way to stand still, but there's 2 ways to move, forward or backward. So we're going to have a lot of these double degeneracies. And again, as the quantum numbers go up, our energy levels become increasingly separated. And this means in terms of, say, spectroscopy, it's going to take us more and more energy to jump levels. So it's going to be very easy to go in between our ground state and our first excited state, but harder and harder to go up from there. However, it is worth noting that we can use these same basic sets of wave functions and our permissible energy and our permissible quantum states to not just examine energy, but also examine that motion more directly. And this will really help us interrogate that positive and negative m sub l. And we can do that by pulling out our angular momentum operator. So again, just the angular momentum in the z direction. One of the things I do want to make note is I've been using a J value for the operator. Your book tends to use L, and one of the reasons why is that this is the operator that tends to be used for atomic rotations, which we're building up to. J tends to be used for molecular rotations, but both of them are going to be equivalent, and something you should keep an eye out for is kind of rampant all over the PChem world, is inconsistent notation. So I'm going to try and keep consistent with a J. If you see this L operator, it's the same thing. Now, we can use this new angular momentum operator, again, in the z direction. We're only looking at the z direction to apply to our new wave function. So we can then essentially take the first derivative with respect to phi. So at this point, 1 over 2 pi comes out front. And we're actually lucky. This is a pretty easy integral. I'm going to pop out an I and an m sub l and then leave the phi alone. So from here, I can then look for cancellations. So we now introduced an I, so that's going to cancel out with the 1 brought on by the as the prefactor for the operator. And we're just left with h bar over m sub l over the square root of over the square root of 2 pi. Now, because we're looking at an operator system, we want to make sure we've properly identified our wave function. So our wave function is actually the exponential over 2 pi. So we can incorporate that back into our original wave function. So all we're left with as an eigenvalue is our quantum number times h bar, which hopefully should look familiar because we found very similar results when examining a one-dimensional free rotors, whether they were confined or not. Now, as a result, this is kind of cool because it means our angular momentum can have positive or negative values. Because if I have a quantum number of 0, so ground state, no movement. First excited state, I can move forward, positive angular momentum, meaning I'm moving in a clockwise direction, or negative angular momentum, meaning I'm moving at the same speed, but in the reverse direction. So this is one of those important things to make note of. When we have that positive and negative and that quantum number, this is going to tell us a lot about the direction of movement. So the number itself tells us a lot about speed. Sign tells us about direction. And this ends up giving us kind of a cool introduction to two-dimensional movement and a lot of rotating references, which becomes really important when we build up the atoms, as well as looking at rotational spectroscopy. However, I want to take this as an opportunity to kind of review some of the lessons from our basic rigid rotor. First of all, make note that energies and momenta are going to be quantized to integer values. And this is actually really important because we usually don't think about translational and rotational motion in a molecule being quantized, but it turns out they are. And more importantly, using our quantum numbers, we can actually get a lot of information about the direction of movement. So this is going to become a little bit more important when we're talking about, because we have moving charged particles, it turns out that this angular momentum can play a big role in magnetism. So this is an important thing to note when we're talking about rotating charged particles. And again, if you need help refreshing what direction a system is moving, always go back to your right-hand rule. Also, want to make note that at least for movement in 2 dimensions, energy does not actually depend on the sign, but what the sign does, but the influence of the sign on energy is going to be a double degeneracy of all of our energy levels besides the ground state. And finally, higher energy levels indicate a faster oscillation because higher rotational momentum, and also they're going to result in higher energies. And these separations in between the angular momentum and the energies are going to increase at higher and higher levels. So we tend to reach kind of this maximum sort of energy level. And as a review of StatMech, that's going to be largely temperature dependent. So this kind of brings us to a summary of 2-dimensional systems. Next time, we got to go to 3 dimensions. Till then, take care.